So just a minute, let me open. We had solved. So we had discussed about torque and back EMF in a DC motor. So I started by explaining the working principle of DC motor. Then we looked at the back EMF and then generated EMF, and then we solved some problem on that. So this is an example problem. So the data of the machine is given and you're asked to find out the back EMF, copper losses, friction windage losses, and so on. So this is this thing. And typically for solving DC machines, I introduced two types of diagrams. So as you know, one is a circuit diagram that you are seeing on the screen. So other one is a power diagram. So different stages of power you can see in the diagram. So on the right side there is the input electrical power, on the left side is the mechanical output power. And then we have done a brief verification also in the last class. Then we continued to look at more problems. So for example, in this, so example 20, so DC machine data is given and then determine the electrical power when working as generator and mechanical power when working as motor. So both ways it does. Then in the generator connection, you'll notice the current directions. So EG will be more than the terminal voltage. So if terminal voltage is 250, EMF generated will be more. Therefore, the current direction will be out of the machine. Whereas in the motor connection, look at it, the back EMF will be less than the terminal voltage, and therefore the current direction will be into the machine, and the shunt field current and all KCL appropriately you will have to apply. So this is a torque developed expression. So we had one or two expressions for torque developed, so that also it is shown here. And then I think finally we got these three equations for determining the armature torque of a DC machine. And then after that, again we can use the power diagram to know about the shaft torque and the armature torque. So if you take the power developed, then from that you can find armature torque, and if you take the power output, from that you can find the shaft torque. So we had done that. Then continuing on, so we had one more final problem that we worked out, that is to actually find out the armature torque and shaft torque. So you have a 220 volt 4-pole series motor and all the machine details are given, and we have to find the armature torque and shaft torque. So again the same method we followed. Draw the circuit diagram and draw the power diagram, and from that you can find the armature torque and shaft torque. So these were some of the problems. So I have shared all the lecture notes with the MOOCs coordinator. So you will be, I think after logging into the website, you will be able to download my lecture notes. And anyway, you are taking class notes, so you can, I strongly suggest you don't keep it pending. Regularly do practice, because this subject is practice based subject. So if you practice the problems regularly, you will not find any problems later. But then all of a sudden, if you, without practice, if you look at a question, it will be confusing. So the more you practice, the more stronger you will become in this subject. So before I start today's class, so maybe I'll wait for a couple of minutes. If you have any doubts, feel free to ask your doubts. So today we are going to talk about characteristics of DC motors, but then I'm just giving you a couple of minutes time. If you have anybody have a doubt, please feel to ask. So there was a comment that voice is not coming. So are you able to hear voice now? Now. So what do you mean by characteristics? Already you had seen characteristics of DC generator. So characteristics means you are trying to get the performance of the machine at different conditions. So for coming to the motor characteristics, so there are basically three types of DC motor characteristics. So what are the three types? So the characteristics, first one is torque versus armature current. So in this, what we do, on x-axis there will be armature current and the y-axis there will be the torque. Second one is speed versus armature current. And the third one is the other two, that is torque versus speed or speed versus torque. So this is the three different characteristics, and we have different machines. So different types of machines. What are the different types of machines? So DC motors. So I have shunt motor, I have series motor, then we have, so three different types of motors are possible. Again, in compound there will be added, additive and subtractive. So we'll come to that. So I have like this a tabular form. So where we'll discuss each machine and look at what are the torque versus armature current, speed versus what are these characteristics. So this is the task. So let's go to it. So let's look at the shunt motor. So even before we do that, so you already know that we had derived the expression for torque of the machine, and the torque of the machine. So if you refer to the previous class, the torque of the machine is proportional to the product of flux and armature current. So let me give you that actual exact expression. So we have TA is equal to So this is the expression we have already derived. So we have already derived in the previous class. So this tells that armature torque is proportional to the product of flux and the armature current. So because Z is constant, P is constant, A is constant, 2 pi is constant. So if I just remove all the constant terms and keep only the variable terms, then the armature torque is proportional to the product of flux and the armature current. So therefore, if armature current increases, torque increases. Therefore, similarly, if flux increases, torque also increases. So this is the kind of basic characteristic of a DC motor. Now coming to shunt machine. So in shunt machine, the field voltage is usually constant. So equal to terminal voltage. So remember how we connect the shunt machine. So this is the field winding, this is the armature resistance, and this is the armature of the DC motor, and then I have electrical source. So this is the voltage source, and this voltage source voltage is directly applied across the shunt field winding. So therefore the current ISH will be nothing but V by RSH. And V is constant and RSH is constant, therefore shunt field current is constant. Therefore flux is also constant. So the IA may increase or decrease, that happens in this branch. So therefore torque is proportional to flux and IA, but now because flux is constant, therefore for shunt machine torque is proportional to IA. So this is the main point about the shunt machine. So therefore if I want to draw armature current versus torque characteristic, it will be like a straight line like this. So this is the torque developed in the armature, TA. So there will be some mechanical losses. So if you consider that losses, then this dotted line will represent the shaft torque. Shaft torque and armature torque. So this is the relation between the armature current and the torque of a DC shunt motor. Now similarly, what about the speed? Now what is speed proportional to? So now you look at the speed. Speed is proportional to the product of actually back EMF. Back EMF is proportional to product of speed and flux. So therefore, speed is proportional to EB by flux. That means the speed of the machine is directly proportional to the back EMF, inversely proportional to the flux. Now, in the case of DC machine, DC shunt machine motor, flux is constant and EB slightly reduces. So reduces with increase in IA. So because when the armature current increases, there will be a drop in the armature resistance. So again, if I go back to the diagram, so this current is IA. And this resistance is RA, and this drop is back EMF. So from this, I can tell that so IA is pointing upwards because IA is pointing downwards because it's a motor. IA is pointing downwards. Okay, so therefore EB is equal to V minus IARA. So EB will be less than V. So therefore, if IA increases, EB decreases. But then, because of RA is a very less value, the reduction is not severe. So therefore, the speed and armature current characteristic of a DC shunt motor will look like this. So this is armature current, and this is speed. So it will look to be slightly drooping characteristic. Straight line, slightly drooping. So this is the y-axis is speed and x-axis is the armature current, and it is slightly falling. So how much will be the fall? So if you consider, so this will be typically 90% will be the fall. This is only a typical number. So small 5 to 10% variation will be there in the speed of the DC shunt motor. Now, depending on these two, so I have IA versus torque, and then I have IA versus speed. So torque and IA are almost proportional. So therefore, I get torque versus speed characteristic like this for a DC shunt motor. So with this, we conclude the characteristic of a DC shunt motor. So let me just update it in the above. So x-axis is IA and y-axis is torque. So whereas here YA and here is speed, and last one is nothing but torque versus speed. So what we discussed just now, this is going to be a straight line, this is going to be slightly drooping, and this is also slightly drooping. So this is a characteristic of a shunt generator. So any doubts up to here? So just take a minute. If you have any doubts, feel free to ask. So I hope there's no problem with my voice. As some of you, if you find problem with the voice, please check at your end. If nobody is able to hear me, just let me know. So I'll just give a break of 1 minute. Just try to think about this. Just I'll be continuing. If you have any doubts, please feel free to ask. Okay, so now the question is, what are the applications of DC shunt motors? So if you look at the characteristics and if you look at the speed, you see speed is almost constant. So if the speed is 100% here, it's just varying very slightly. And that too, if you consider a particular load, then the speed is constant for that load. So therefore, it is used for constant speed applications. So what are the constant speed applications? So for example, in the industrial use, so lathe machines, then we have drills and spinning machines. So you can use it in the paper industry, etc. So wherever there is a constant speed application, you can use the this thing. So woodwork, etc. So these are some of the applications of DC shunt motors. So now let's come to DC series motors. So DC series motors, see we know that torque is proportional to product of flux and armature current. So whereas in DC series motors also proportional to IA. Field is proportional to, so this is in series machines. When there is no before saturation. So therefore, torque is proportional to Ia square, because I can replace Ia by one more Ia and it will become Ia square. So this is before saturation. And once the magnetic poles are saturated, any further increase in Ia will not increase the flux. So therefore, torque is proportional to Ia after saturation. So given this information, now I can plot the characteristic. That is, on x-axis I have Ia, on y-axis I have the torque. So initially it will be like a square, then it will be like a straight line. So this is armature torque of a series motor. So this is armature current versus torque characteristics of a series motor. Now what about speed? Now we know that speed is proportional to EB by flux. Now this flux, if the flux is low, that means speed is very high. But since it is a series machine, in a series machine, flux is low means Ia is low. That means no load. So therefore, if actually it is no load, Ia is 0 and flux is 0, speed will be infinite. So therefore, at light load, or at small loads. Speed of series motor is dangerously high. So therefore, always care should be taken that the series motor should never be started with no load. So if I look at the plot, so it will be speed versus armature current, and the plot will be like this. So when the armature current is close to zero, speed is infinity. But when the current is increasing, speed will reduce and it will be maintained at a particular speed as it is shown here in the diagram. So this is about the relation between speed and torque of a characteristic between, sorry, speed and Ia of a machine. Now same way, since Ia is proportional to torque and square of Ia is proportional to torque, we will get the similar relation, that is so on x-axis we will have torque and y-axis we have the speed, armature torque. And for the series machine, so this will be again something like this. So for it can generate very high torques at small speeds, but at very small torque, very high speeds it is possible. So again, to summarize, I'll just go back to the first table. This is Ia and this is torque. Similarly, this is Ia and this is speed. And finally, this is torque and this is speed. And the characteristic, it looks like torque versus Ia increases like square and then straight line. Whereas this is like this is like this. Okay, so what are the applications? So let me go down and then write. So what are the applications of a DC series motor? So you notice, look at speed. Speed is not the constant, speed is variable. High speed to low speed it can support, like this. So what are the applications of a DC series motor based on the speed? So of course it is a variable speed application. So first one is electric trains. So what happens in electric trains? Look at this diagram. When the speed is low, so take this point. When the speed is low, very high torque is generated. So that very high torque is useful for starting of an electric train, and slowly the electric train gathers some speed and the speed starts increasing. And when the electric train is running at very high speed, at the time very low torque is sufficient. So this is N1, this is N2, and this is T2 and T1. So when the train is going at very high speed, less torque is sufficient. And then is it possible that the torque will be very, very low? It is not possible, because always some load is connected, because it's an electric train. So there is no danger of train going into dangerously high speed because of no load. So one application is electric trains. So similar to that, any application where there is a variable speed is required, then we can use this applications. So for example, cranes, and we have elevators, miners, in fact your grinders. So in the kitchen we use a grinder. So that grinder is actually a DC series motor or even a AC series motor. It can work on AC also. So these are some of the applications of a series motor. So any doubts up to here? Okay, so let's now discuss compound generators. Now look at the compound generators. There are two types. So one is, so of course you had seen long shunt and other is short shunt. I'm sorry, this is generators or motors. Now this is based on connections. Now also you can have compound motors. So again two types. One is cumulative and the other is subtractive or differential. So what is cumulative? So this is based on polarity of the field. So for example, if you look at this, so let's say, so now you have shunt winding. Then we have a series winding. So the series winding, for example, if it is like this, so this is connected in series with armature. So now you notice the flux created by this, if it is in this direction, the flux created by this may be in the opposite direction. So this is flux due to shunt field and this is flux due to series field. Therefore, resultant flux will be, of course, whichever is high, based on that it will be there. But then this particular connection will reduce the flux. So this is called differentially compound. Compound connection. So therefore, as IA increases, flux decreases. So this is the nature of this particular connection. So if I keep the shunt flux constant, as more IA I pass, the weakening the flux will become. So this is one connection. So another way to connect, of course, is the opposite way. So you can connect both in the same direction. So for example, this is both in the same direction. So this is series field and this is shunt field. And both of them are adding with each other, phi SC and phi SH. So if this is the case, then it is a cumulative compound machine or motor. So here IA, if IA increases, flux also increases. So what is the total flux? Total flux addition of these two. So if IA increases, flux also increases. So this is the relation. So keeping these two relations in mind, you notice that the characteristics of DC compound motor are in between that of series and shunt motors. So let me explain what I mean. So this is an important point. So the compound motor will have characteristics which are in between. So in between that of series and shunt motor. So if I have a shunt motor characteristics and if I have a series motor characteristics, I can find the in between for that. So for example, I have IA versus torque. So it is a straight line in the case of a, this is a shunt motor. Whereas in the case of a series motor, it's like initially a square and then followed by a straight line. So this is series. So this is shunt. So the characteristic of compound will be in between them. It exhibits the behavior of both shunt and series motors. So this is cumulative compound. So whereas if you look at the other side, this is the differential compound. So this is the torque versus IA characteristic. I'm sorry. So let's look at the speed versus IA characteristic. So this is armature current and this is speed. Now you know that speed is drooping in the case of a, sorry, this is shunt. It's almost constant, slightly it is varying. And what is the characteristic of a DC series motor? Series motor characteristic is like this. At low values of IA, dangerously high speed, and then actually the speed falls. So therefore, the middle characteristic. So this one, what I just shown is a series. So somewhere in the middle, I'll get the characteristics of that of cumulative compound. Similarly, you will get another characteristic which is above. This is differential compound. Now you may ask the question, how come the speed is increasing when the load is increasing? So of course that is a characteristic of differentially compound, because when the look at the differential connection. So when the load is increasing, IA increases, flux decreases, and the moment flux is weakened, speed is picked up. So speed increases. So that is why this is the characteristic. The speed can increase. So I think these two are the characteristics of the machine. So now differential compound is actually not that much useful. So is not used much in industry due to poor characteristics. See here the speed is increasing with increase in the load, so that is not expected. So such kind of thing will not be used. So what are the applications of cumulative compound? So cumulative compound, see it has both characteristics of series and shunt. So that means it can be, so it has both, it is like a speed is constant but not that much variable. So, but not that much constant, slightly variable. So it is useful for intermittent loads. Or in other words, sudden loads. So here, for example, punching machines. So you want to, in a metal, you want to punch some holes. Then for the punching machine, we use this. It's also used in coal conveyors. So you want to transport very heavy coal from one place to other place. You have a conveyor belt. So for that functioning of that, so anyway, I think we'll not go further in this. So just again have a look at this, and if you have any doubts, feel free to ask. I'll just again give you 1 or 2 minutes break. If you have any doubts, feel free to ask. Table taken from the Electrical Technology Volume 2 BL Tereja textbook, and in this table, First column is the type of the motor: shunt motor, series motor, and cumulative compound motor. And in the second column, what is the characteristic? And finally, last column is the what are the applications. So again, just have a look at this. This is kind of a review of what we have done so far. So I'll just give you a couple of minutes time. If you have any doubts, feel free to ask. In self-excited, DC generator is dash. So the options are, so additive, I'm sorry, this is difficult, what are the options?